In fact, I can't even master agree. Yeah, okay. Recording. This is a meeting interview. No problem. You guys go on.
All right. Good morning, everyone. My name is Michael Abiona, master's student in the Department of Computer Science at Strength University. So this morning, I'll be talking about my work right throughout the semester, the reading course, and the topic is efficient triangle connected Truss community search in dynamic graphs. So firstly, what are graphs and what's a graph, right? A graph is a mathematical structure used to model relationships between pairs of objects. And a graph will consist majorly of a node and an edge, right? So the node are the individual objects, while the edges are the connections between the nodes. So graph can represent a wide range of systems, such as social network, biological network, and computer networks. And we can see an example of graph in our real world scenario, such as in a school system, right? In a social media, like social media, right? Such as in LinkedIn, Facebook, Twitter, and Instagram, right? So they show connections. So, and we have different types of graph and algorithms. So quickly, there are so many types of graph. So I've just listed three here. So I have the directed graph, the undirected graph, the weighted graph. The directed graph, according to the name, shows that the edges, right, shows direction. So they have arrows pointing to the direction of the from one node to another, right? While the undirected graphs don't have directions, right? They are just as shown in the picture. The weighted graph have weights on their edges, right? They have weights on their edges just to show the weight or the quantity or the length of the edge. So then we have graph algorithms. There are so many graph algorithms. We have the transversal algorithm, such as the breadth first search, the depth first search. You have the shortest path algorithm, such as the Dijkstra algorithm. And in the picture on my far right, I showed us an example of the shortest path algorithm scenario. I'm very sure most all of us use Google Maps every day for our navigation and all of those things. So in Google Maps, when we enter our destination, right, it's going to calculate the shortest distance between our current position, and then the destination, right? So that's an example of the shortest path algorithm. So then we have the K-core and the K-truss. So the core of my research is on K-truss, and I'll be talking more on K-truss very, very soon. So the research motivation, right? Why should you listen to me today in my research topic, right? So I've explained that graph can be, we can see example of graph in social networks such as Facebook, right? And social networks such as Facebook have billions of users, right? According to research, I think Facebook has over 2.9 billion users, and we want to be able to search, right? So, for example, we want to look for someone bearing Daniel, right? Like in the picture on my far right, that's my Facebook account. I was searching for someone bearing Daniel. So, in order to be able to search, we need to have a fast way of searching um, individuals or persons in a database. So, take for example, Facebook that has 2.9 billion users. Um, if we don't have a way to search efficiently, right? If I search Daniel, it may take me hours to get that result because there's no efficiency and because the database is large. So our solution, the equity tree index, provides a more efficient way of querying graphs and discovering communities in a graph. Also, we can see an example in fraud detection also. So in fraud detection, we can analyze graph to detect fraud and connections around that fraud scenario. So presentation overview, right? My presentation will be talking more. I'll be giving us some backgrounds on the presentation. Then backgrounds include K-truss, trust decomposition algorithm, and I'm talking about trust maintenance, triangle connected K-truss community. Then in the main topic, I'll be talking about the search problem. So what's our problem? Because in order to provide a solution, we need to have a problem, right? Then I'll be talking about the equity index, which is the solution that we are proposing. I'm talking about the equity construction algorithm, the space-time complexity of the equity index, the index maintenance, and experiments and results, and then references. So what is a K-Truss? K-Truss is a subgraph where every edge is contained in at least K minus 2 triangles. So when we talk about a K-Truss, we are talking about the graph, right? And when we talk about K-Truss, we are talking about edges. We are dealing with edges. So what do we mean by K minus 2 triangles? For every edge, take for example our example graph now. If we let me show. Okay, so the higher the value of K, the more connected the more triangle connected the edges. So take for example, from my example graph now, if I pick edge V1, V2, right? So that's an edge. You can see that it forms a triangle with V3 here. Then if I take another edge, we can see that that same edge V1 forms another triangle with V4. So that makes that edge V1 a 2 triangle edge, right? So that makes it a 3 truss edge graph because 3 minus 2 is going to give us 1 triangle, right? So this is 1 triangle. So initially we have 1 triangle, right? So when I added the other one, when I added the other node, that edge becomes a 2 triangle edge graph. So the entire, from our example graph, the entire blue graph, the entire blue edges are the 3 truss edge. The green edges, sorry, the entire tree, the green edges are the 3 truss edge, the blue edges are the 4 truss edge, and the red edges are the 5 truss edge graph. So if we do the same calculations across all the graph, I can't do that because that's not the major of our research. You'll see that we're going to get that as the green ones are the 3 truss edge, the blue ones are the 4 truss edge, and the red ones are the 5 truss edge. So to trust K-truss decomposition, what do you mean by K-truss decomposition? Decomposition actually means reductions, right? So when we have a graph, we want to discover communities. We want to discover structures that are tightly connected. So that's why we perform K-truss decomposition on a graph. So when we want to do K-truss decomposition, we definitely have our example graph, right? Then we start with the old graph and increase the value of K. Don't forget that we have our K is the truss number of the edge. So we increase the value of K. As we are increasing, there's going to be a pruning process that will be going on the graph, and the graph will be reducing, right? So the remaining graph will be the K truss of the graph. So take for example, this is our example graph now, and it's a 3 truss edge graph as it is like this. So if we do the pruning, if we do the pruning, so increase the value of K, right? So it becomes a 4 truss edge graph, or yes, a 4 truss edge graph. Then if we increase it further, right? So this is the first decomposition process. If we increase it further, it will become a 5 truss edge graph. So, and this is the highest that we can go because if we prune it further, we are not going to have anything again. So this is the highest that we can go. So this is the K is equals to 5 is the highest that we can go with the decomposition process. So the overview of the period decomposition level. So the entire graph, the 3 truss edge graph. Then
sorry, can you remove this? Remove so you can see the screen. Now remove. Move to the sidebar. Move to good. Cannot see the graph. Continue.
Yes. So the entire graph is the 3 truss edge graph. The one on the far right, the blue one, the 4 truss edge, after the first decomposition process, and the red one is the 5 truss edge when we decompose further, right? So next slide. So we want to talk about K-truss maintenance. K-truss maintenance graphs are generally dynamic. So and graphs, real-world graphs are generally dynamic. So there'll be a lot of insertions and deletions going on a graph. So we want to be able to maintain the graph, right? And to achieve efficiency without recomputing, to achieve efficiency without recomputing the whole graph, you want to be able to capture sections that are experiencing removals or deletions in a graph. So take for example, edge insertion now, right? If we insert an edge to this our example graph, take for example, V1 to V9, right? We are going to see that the truss level of that section, of the circle section is going to change, right? So we see that that one is going to change to a 4 truss edge graph, and the V8, V9 is going to change to a 5 truss edge, right? So we are going to, so edge insertion maintenance is calculating the section that has changed instead of recomputing the entire graph. So the same thing goes for edge deletion. If we delete this edge V3, V5, we'll see that the truss level of the triangle of the circled section is going to reduce. So V3, V4 is going to reduce to a three truss edge, while V4, V5 is going to reduce to a 5 truss edge. Then we want to talk about the time complexity. Time complexity, time complexity for edge insertion is as given as that. So it's the minimum degree of the U and V, right? And that's for the average case. And for the worst case, it is going to recompute the entire graph. So we don't want to have that worst case. We want to work with the average case or the typical case. And it is unbounded because we can have multiple insertions on a graph. But for edge deletions, it is bounded because edge deletions, it is bounded. There's a boundary. We can't have we can't have more edge deletions than the edge we have in the original graph, right? So that's why it is bounded.
Question: when the average case happen and when the worst case happen? You see the average case and the worst case.
Yes, the average case is recomputing for the section that has changed, right? So it's like the complexity for recomputing for the sections that has changed. But in the worst case, right? Worst case is like recomputing for the entire graph. So the truss maintenance is like for the worst case is computing for the entire graph.
Sorry, I mean in which kind of graph? Which kind of common our social network graph?
Yeah.
It's the worst case or average case?
It depending on the scenario. It depending on the scenario. It depends on the number of insertions that you're having, right? Or deletions, right? It depending on the scenario that you're having. If you're having a lot of insertions at the same time, right? That it's either hard to compute each sections at the same time, right? Then we are going to have a worst case. That's computing the entire graph.
Not correct. Sorry. And worst case happen is a very special graph, like chain graph. The graph is a chain.
Okay.
It's reduced to a line. It's a graph, but it always has a worst case because when inserting and removing, will traverse the whole graph.
Okay.
But average case is all our common data graph, like social network. But is average case.
Yeah.
Worst case is always to some very special graphs.
Yeah.
It's a graphs. To different kinds of graphs, it's different kinds of graphs can be average case or worst case.
All right. So so that's the time complexity for the end insertions and deletions. So after that, we move to the what we call triangle connected K-truss community, right? So in the aim of our research, the reason why we do decomposition is for us to determine communities in a graph. So take for example our example graph, and after the decomposition process, we arrive at these two graphs, right? So we arrive at these two graphs. This is a K-truss. This is a K-truss graph. This is a triangle connected K-truss graph, and the other one is a K-truss graph. So this is after the first decomposition process. We obtain that K-truss graph, right? But there's a problem with this graph. This graph is not a triangle connected K-truss community. Why? Because it cannot reach edges cannot reach each other via a series of edge adjacent triangles, and there exists a cut vertex here. So that V4, the arrow there is the cut vertex. Because why is it a cut vertex? It is a cut vertex because when we remove that vertex, it's going to split that graph into two. So that makes that graph vulnerable. So it makes that graph weak. So it is not a triangle connected K-truss community, whereas it's a K-truss graph. So a triangle connected K-truss community is more connected, right? There's no it's more connected than the K-truss graph ordinarily, right? So then we are going to look at the diameter upper bound of a K-truss, of a triangle connected K-truss community, which is for short KTTC, right? So the diameter upper bound of a KTC, it is more cohesive, it's more bounded, so it is more well connected than that of a K-truss subgraph, right? So that's the formula. It has been determined, right, through research. So the observation is that the KTC has a tighter or at least equal diameter upper bound compared to the K-truss. So in the previous example, I showed us that the K-Truss is weaker because of the cut vertex, while the KTCC is more cohesive.
Good.
So to the community search problem, so this is where our research starts from, right? So the search problem. So given a graph with K-Truss K and a query vertex, we can perform a community search to retrieve meaningful communities with respect to the query vertex. So when we are talking about the search problem, we are going to be working with the query vertex and the Truss number. So when we are given a query vertex and the Truss number, we are to determine, and we are asked to determine the community around that query vertex. So what we are going to do, the first process is to do the decomposition, right, to the Truss level, that's to the Truss number, to the Truss level, that's K, right? So, and then with our query vertex, we are going to determine the community surrounding that query vertex. So in our example here, so this community surrounding query vertex V7 we have two communities, so the 4 Truss community and the 5 Truss community. So this is an example now. So given K is equals to 4 and VQ is equals to V7, we can derive the 4 and 5 Truss community. So these are the previous from the previous slide. So if we split this community now, so we have those, right? So the one at the top are the 4 Truss community, right? Because we have the minimum edge we have there is the 4 Truss edge, and the twos at the top are the 4 Truss community, while the ones below are the 5 Truss community, because the minimum at the top is 4 and the minimum at the bottom is 5, right? Sorry. Yes. So the equity index now. So we have determined we have stated the problem, our problem, right? So we want to be able to discover community and to query a community by.
Why would you need the equal tree?
Yes,
why the query need this equal tree?
Yes, because we have a problem here, right? We want to be able to. We have determined the community in the graph, right? And we want to be able to query the community, right? And in order to be able to query the community, we don't want to traverse the entire graph, right? Because it's going to be very, very slow, right? We want to be able to get community in the minimum, in the smallest amount of time that we can get. So we can do that with K-Truss, but it's actually very slow. So the equity index is the state of the art, right, method to perform efficient community search query on a KTTT. So that's why we need the equity index. So from our example, in order not to bore us with too much words, so from our example, equity index pass through 3 phases, right? The first thing is to determine the equivalence class from the graph, from the main graph G, right? Then from our class, then we do what we call Truss precedence and node merge. Then we derive the equity itself, right? So from from our diagram, right, we can see that it is easier for us to query or to search through this tree than for us to query the entire graph.
Can you show us how can we query in this equal tree?
Yes, I'm going to explain. Yeah. So before that, I'm going to show us how we derived this equity tree, right? Just to show us because this is actually the core of our research. So the first thing is to derive the equivalence class, right? So this is our example graph, right? These are example graph. The first thing to determine the equivalence class. So for each Truss level, there are equivalent classes. So I've explained earlier that the green edges are the 3 Truss edges, right? So and we can see that we have 3 sections of the blue edges. So that makes us have 3 equivalent classes, right? C means equivalence classes, while K is equals to 3. So the 3 that we have here, so the C31 means the first one, C32 means the second one, C32 means the third one, right? So C31 is gotten by, so V3, C31 is V3, V5, right? So this C31 here, this C32 here, V10, V11, and C33, V1, V8.
Why, sorry, question, why they are separate? First one, second one, third one, why they are separate?
Yeah, because we have three different classes for that.
I see the Y is you say it's a this and this is a separate and it's connected with this H.
Yeah, yeah, it is connected with the entire graph.
Oh,
Yes, but we want to want to split it into class, right? What we are trying to do is to have an equivalence. We want to derive the equivalence of this entire graph. And in order to derive the equivalence, we need to put these trust level edges in different classes.
okay, must be
Right.
connected.
Yes. So they have to be in different classes, and then I'm going to put them together.
Okay, yeah.
Right. So for the four trust level, right? So these are the classes. We also have three, right? For the four trust level, we have C41, right? And C41, we have B5, B11, right? So how this is calculated is like when we start with this, we start with the smallest value, that's B5, because B5 is the smallest here, right? So B5 to B6, you have B5 to B7 and B5 to B11, right? Sorry. B5 to B11, B6 to B11, and B7 to B11, right? So the same thing goes to C42 and C43, right? That's how those are calculated over there.
Okay, good.
So the same thing goes for the when we decompose further, we are left with the 5 trust edge graph, right? So the equivalence class is also calculated as such. So we start with B4, right? B4, B5, B4, B6, B4, B7, then we move to B5, right? B5, B6, we can't go B5, B4 because we have already done B4, B5. So B5, B7, B5, B8, right? Then we move to B6. We can't go back B6, B5 because we have done B5, B6. So B6, B7, B6, B8, B6, and then you move to B7, B7, B8, right? Those are the last. So that's how those are connected. So then we can see our entire graph, right? And it is converted. We can see the conversion now to the equivalence class. So this is our equivalence class on the right.
Good.
Right. So so I've listed out the equivalent class here in the table, and we can see how they are connected as well. They are connected.
Question: can we directly query in this equivalent class?
No.
So you say we can query from the graph is too slow. Can we query from here?
Yeah, I think we can do that, but the research didn't talk about query from here.
You sorry?
Yeah, I think we can do that.
We can do that, yes.
Yeah, they can definitely do that as well, because this is actually the equivalence class.
Equivalent class.
Yeah,
I think I can do
yes, yes. So it's actually the equivalence of the graph. So we can see that it's even smaller. We can see that
much smaller.
Yeah, if we query on this equivalent class, it will be more faster than querying on the entire graph. Right? But that's not our end game. But I think this is where the other solution that we have, the previous solution that
previous solution.
Yeah.
Very ready to work.
Yes. So this is where they stop. But the equity went further, right? The equity went further, and I'm going to be showing you how we derived that. So the equity went further from converting the equivalence class to something. So it implements what we call trust precedence and node merge, right? So how it implements this is that it started from highest class, that's C5, right? So we form it as a node, right? So which is A. We move to the higher class, so C4, C41, C4 to C43, right? So and if we check this C41, this C5, right? And when we see that, so that's why they are connected like this. So see that triangle connected, there's going to be a conflict here, right? So what we do is we merge it together, right? C41, C42, we merge it together and connect it with C5, right? So we have those there. So then we move higher to the list level, that's C3, right? So we have C3, C3, C31, C32, C33, right? Then those are also triangle connected with this. We can see from this diagram that is triangle connected with this. Yeah, we can see that it's triangle connected with this, right? Also, there's going to be a conflict here, right? So because of that conflict, it's going to merge. Those three are going to merge and also form a connection with C4 and C42 and C43. We can see that forms a tree. So that
why this edge can merge into the tree edge? So this
So C31 is trying connected to C41, C42, and C43.
Yeah.
Also, C33 is trying connected to C41, C43, while C32 is connected to just this, right?
Okay, so I can merge together.
So it's going to merge together, right, to form the tree. So we can see that the tree structure is a much smaller structure than this equivalence class, and that will make our query also faster than this, right? And this will also make it faster than the original graph.
Yeah.
Right, you can see these are example graph, and this is the equity equivalence that we got. So
this was a query example in this two query example. Like, can you show the query example? For example, I want to check V1 and V4 is in the same chart community or not. V1 and V4.
V1 and V4.
Yes.
We want to check this.
Oh, make it harder. V1 and V10.
Yeah. V1 and V10.
Yes.
Okay.
In the original graph, it must traverse the whole graph. Yes. Almost the whole graph.
Okay. So first of all, we can see that the entire V1, V2, V3, V4 are 4 truss edge, right? And also we can see V7, V8, V9, V10, and in fact, all of these they are also a 4 truss edge, right? And they are trying connected to the 3 edges, right? So in our equivalence class, right, in our entire tree. So we want to traverse this, right? It's just like you want to traverse from V1 to V11 or V1 to V10. It's just like traversing between V1 and V2, right? So instead of going through V1 to V8 to V9 to V10, so we don't need to even get to this, right? We just only need, so everything is just between these two, X1, X2, and X3, X4.
So we need to check that from this one and this one.
Yes. So the blue ones, that's X2, X2, X4, are actually the 4 truss edge level, right? While the X1 and the 3 truss edge level. So this has been compressed, right, to this X1 here. Whilst the blue ones are compressed to X2 and X4, whilst the 5 truss edge is just the X3.
And that's really fast. Yes, the equal tree is compressed at 3 nodes.
Yeah, it's compressed, yes.
Yes, great.
Yeah, so we can see that it will be faster for us to query that tree than to query the entire graph. Right. So this is the pseudocode, right, to construct the equity algorithm. So there are 2 steps involved here. So we have the Truss decomposition and the equivalence class conversion.
Why is there type complexity is m power of 1.5?
Yeah, I'm going to show that the next slide. So this is the pseudocode, right? So we have the section, the Truss decomposition section, and the equivalence class conversion, right? So this is the code to do that, right? And also we have the node merge and the tree conversion, right? So like I said, there are 2 phases. The graph converts to the equivalence class, and the equivalence class converts to the tree itself via that function. So this is the entire code to run that, and the entire time complexity is O of m power 1.5. So this
why? Can you explain why?
Why? Because
briefly explain why. I understand it's m, but it's why m whole power of 1.5.
Because
where did the 0.5 come?
So because Truss decomposition itself, the time complexity for Truss decomposition itself is m.5.
It comes from Truss decomposition.
Yes.
Why?
Because that's what has been from research. Truss decomposition time complexity.
Go on.
Yes. So and the next stage, right? Which is the conversion to the tree itself.
The node merger is m. What is x?
So I've written it here. X of m is the inverse Ackermann function. So it's actually a kind of function, right? And we can want to read more on that, we can check this paper. So to check
the node merge will traverse all of the vertices in the node. Right?
No. So when we get the equivalence class, right? So and like I explained earlier, can I go back?
Yeah, yes.
Yes. Okay, sorry. Yes, so this is the section for the node branch, right? Like I explained earlier, we start with the highest class, that's C5, right? So we have that. So we have only one C5, so we just only put that there, right? So then we move to the next class, right? So that's the C4 class. So we have C41, C42, C43, right? So C41, C42, and C5 from this equivalence class, there's a way you can derive that they are
That's my question. So what? Here, C41 and C42 merged together. How much time it spend?
It is that function I showed. That's a command function. So that's the time.
The common function. So I can say it's it must traverse all the edge and merge them together.
Pardon?
Traverse all the edge, C41 and C42, and then merge them together.
Yes. So I think that's what the function does.
Okay.
So that's the entire time complexity of the equity. So our graph, our equity was tested against so many graphs, real world graphs we tested against small graphs with small vertices, 4,000 to 4,000 vertices with 8,000 edges to this graph that has the highest, which is 58,000 vertices, 58 million vertices and 261 edges.
Right? What is Kmax? Dmax?
Maximum diameter.
What is Kmax?
Maximum Truss number. Okay. Yeah. So diameter of the graph, the maximum diameter of the graph, right? The maximum Truss number of the graph. So we tested against these six real-world networks, and we discovered that the Equitrust perform better than the previous solutions, which is the TCP index and Equitrust. So, like I explained earlier, the Equitrust only stopped at the equivalence class conversion, right? Which is actually better than the entire graph, but it could also be better. So the Equitree went forward than the equivalence class. So it performed better than that, right? And we are going to be seeing.
I'm curious. So why is the Kmax is the largest K? Largest K. Why the Kmax is always small, even in this very large graph? Why is it very small?
Maximum Truss edge.
Yeah, K. It's large number of K. Why is it? Why is it even this Weibo this largest graph? Why it's very small?
There are different type of graphs, right? So we can't really. So it doesn't. K, just like an example graph.
No, not example. This is a real data graph.
Yes.
Social network graph. Or Weibo is a social network graph. It's from China. I know Facebook is social network graph.
Yes. So Kmax. So the higher number of K means that the graph is well connected. So this showing 80 mark, it feels that the graph is not really well connected, but it is large, right? It's a large graph, but not well connected. But this one is also a large graph, but it is well connected because it has a higher number of K, right? So the higher number of K shows the connection. So it shows the cohesiveness. Like I explained earlier, the diameter of bubble. It shows the more cohesive, the higher the value of K, the more cohesive it is, or the more bonded it is.
They say it's always small. In social networks, K is always small.
Yeah.
Even the large graphs, K is always.
Yeah. So in this live journal, it is actually large, right? So 352. So it means it's more connected.
Okay, go on.
Yeah. So those are our tested graph. You can see the performance, right? So the comparison. So this is the construction time comparison. This is the Facebook, and so these are the 6 graphs that we tested, and this is the average time.
This is the construction time. Equal tree is not get some not efficient.
Yes. So in the construction time, actually, it's not the best, right? It's actually not the best, right?
Why? Why not fast? What happened?
I think because it takes 3 phases, right? So it goes through the initial graph, does the composition process, and it generates the equivalence class. Then that's the first. So it went to an extra stage, right, of computing the equity. So I think that's why it's a little bit slow in the construction time. Right?
Do you think it's acceptable with the millisecond? Like a Weibo is large graph, but it take 10 power of 6. You get like 1,000 second.
Please, I'm coming in the question.
The 1,000 second, like construct the index, take 1,000 second large graph. It's too slow.
If you compare it with others, you can see that it's still relatively close. It's still close, right? Compared with others, right? Not that, but I think it's just a trade-off, right? We can just trade this off. I think
the consolidation index is very slow. In large graph, very slow.
Yeah, it's very slow.
Like 1,000 seconds.
Yeah.
1,000 seconds.
Yes.
Like 20 minutes, right? 20 minutes. Okay, very slow.
Yeah, it's still very slow. So, but maybe we can improve on that. Maybe
improve by what?
Maybe I mean in the construction time.
Yeah, construction. How can we improve that?
Maybe we can do some more research, like maybe parallelize it.
Yes, parallel.
Yeah. So we can improve the construction time. So, but I think our major focus is just the query, right? So you look at the query time, the comparison with the average query time, you can see that Equitree performed the best, right? Compared with others, right? So compared with Equitrust, the TCP index and the index tree, right? You can see that it is significantly faster than the tree. So this is actually what we are aiming to get, because what we are trying to do is to traverse a graph, to query a graph. Why? Because so you can see the average query for Equitree is faster than the state of the art solution that we have. So a random 1,000 query versus and trust value K as 4 for Facebook, 5 for DBLP, 10 for OCOT and Webhook. So this graph was tested with 1,000 query versus. Yes. So for Facebook, we used K-scores for 4. For B.
So how can we random choose 1,000 query? Okay, good. One is randomly choose the 1,000 query. So some query should be very, in the best case, it can be returned without quickly. Some query need to traverse a tree. Yes, so the random query. Good.
Yeah. So okay. So the point here is that the Equitree is faster than the TCP index and Equitrust, which are the previous solution that we have. Right. So for the maintenance efficiency, we can see also the Equitree perform better for the edge insertion maintenance and also for edge deletion maintenance. So this is the Equitree. So we have the Equitree batch. So we have the Equitree batch and Equitree itself, and Equitrust and Equitrust tree reconstruct.
Oh, it's slow. So Equitree maintain on the Equitree is slow. Oh, Equitree batch is faster.
Yeah,
Equitree batch is faster. So once on the edges together, Equitree.
So there's Equitree batch is also the same thing as Equitree. So it's like a batch. So performing the query in batches, right? So that's what Equitree batch is. So to achieve faster efficiency during maintenance, so it's best to do it in batch, right? Than to do it just ordinarily like that. So the same thing for the edge deletion. So it is best to perform the batch maintenance than just the ordinary.
I think the Equitree batch is faster. I understand. But the Equitree is not always has good performance. Say here, deletion Equitree here is slower than Equitrust.
Yes. So there's something called Equitree batch, right? So it is best for us to perform.
But I know. But if I only want one, I don't want a batch. I only have one card.
Okay.
And one edge insertion and one edge deletion.
Okay.
And I think this case equal trust.
If it's just one edge deletion and deletion, I think it'll be faster than this, right? I think this was performed against many because this we are using real world graph here, right? So it was performed against multiple. It was performed against a large graph, so there's a lot of. So you are just using one, it's going to be faster than this. I'm very sure of that.
Great.
So that's our result. So the Equitree batch has performed the Equitree itself more than one order of magnitude. So that's our conclusion of the presentation. So references, if you want to check read more on Equitree, we can check these papers out. So the efficient triangle connected trust community.
Okay. Can you talk about your future work? So this is reading graph. This is not your contribution. It's this paper's contribution.
Yes.
What can you do in future?
Yes, in future, I want to also maybe do the sequential, like test it, right? So perform real coding, right? I'm going to do the trust composition, the coding and the composition and performing on real world graph, right? Also test this API tree itself, right? On real world graph.
Do you have some ideas? Do you have the idea? New ideas of contribution? Not the experimental contribution in 2 weeks.
Yeah, we can like I suggested earlier, we can do some parallel experiment to make it faster, right? So that's the future contribution we can do. So parallel we can perform the experiment on a multi-threaded system.
That's a good idea.
Yeah. So that's the future work that we can expand on.
Okay, we have 10 minutes left. So I think I asked you all the questions.
Okay, so we can.
Okay, we'll go back to the node merge the node. Yeah, not the algorithm. The algorithm. Yeah. Node merge. Can you explain how much time is spent here?
The time explained is like I explained in the time complexity here. So this is the amount of time.
Yeah, not now I evaluate the time. So now we have 10 minutes left. So can you explain what is that function?
Yeah, so it's like inverse Ackermann function. So it is like this is an entire research on it.
But I don't understand the function. Can you explain in the algorithm how much time it will spend? Is this a constant time, linear time, or some?
It's not a constant time because we have a for loop here. In fact, we have
for
loops, right?
Find a node and then add this A to the tree, and merge conflict with the merge node.
Yes. So we have a for loop here. So when we have a for loop, we don't have a constant time, right? Is sorry.
Oh, two for loops together.
Yeah. So we have two for loops, right? So we have it's mostly it's definitely not a linear time. Sorry, definitely not a constant time, and it's more than a linear time because we have two for loop here, right? So and we have this AUF, right? So this AUF is what is like the Ackermann function, right? Is the research went more on the theoretical part, right, of this AUF. So I didn't want to put that in the slides so that we don't get confused, right? So so the entire section of this node net and tree structure update is the O of M, X of M. So so that's the function there that performs the node merge.
Okay. That's all my question. Good work.
Yeah, thank you.
Do you have any questions? Audience? Ask the question.
No.
Why not ask? That is your ask the question.
Oh, Larry, you have a question?
Yeah, can you do the microphone is the turn on?
What?
Okay, I get to know. Larry, do you have any questions?
No. I'm good.
You good?
Yeah.
Yeah, all good.
All good.
Okay.
Okay, thank you.
Yeah.
And let's take a break. That's 11 o'clock. Let's start. Okay.